Algebraic Reasoning, Chapter 3.2, Exercises 1 through 20. This section, 3.2, has to do with inverses of functions. And usually I've been breaking these up into smaller videos when we do this whole section, the odd number problems. For questions 1 through 4, indicate if the data in each pair of tables represent inverse functions or not. And one of the tenets of inverses functions is x's become y's and y's become x's. And domains and ranges switch, x-intercepts and y-intercepts switch. And here on this left table we have -3, 5. Well, the inverse of that point there would be 5, -3, which is the case. And we can see lining up here, one coordinate pair at a time, that we are switching x's and y's in each of these cases. What you really have to do to be careful, though, is to make sure you look all the way down the table to see that, yeah, okay, x's and y's are switched for each 4 of those coordinate pairs. So, yes, inverse function. Okay, next I'm going to go to the odd number problems here, 3. Okay, here you have 2, 10. Well, the inverse of this point would be 10, 2. That'd be 10, 2, but this is not the case here. And you can see that there are shenanigans played. Here you have, it looks like what they're doing is they're taking that first coordinate and making it negative in each case. But you don't have x's and y's switched at all. So it's just a negative sign. I think what you're doing is you're just reflecting this, whatever it is, whatever points these are here, I don't know what they are, you're reflecting them about the y-axis. So no, not an inverse function. Okay, next on number problem 5. This brings us up for questions 5 through 8. Indicate if each graph represents an inverse function or not. Well, one characteristic you look for in an inverse function is functions that are inverses of each other reflect about the line y equals x. And so if you draw, I'm going to try to draw a dotted line here. Okay, I'm going to draw the line y equals x right here like this. And this dotted. Okay, that's about as good as I can get it. That's going to be y equals x. And you can see, I hope, that these lines are reflections of each other about the line y equals x. Notably, the x-intercept of 3, 0, its inverse is the y-intercept 0, 3. And likewise, this x-intercept here of negative 2 comma 0 has an inverse of y-intercept of 0 comma negative 2. So answer this question, yes, they are inverses of each other. Okay. Next on our problem says, indicate if each graph represents an inverse function or not. Now let's look back at 5. Inverse function or not, they are inverses, but they are also, number 5, functions. Something reminded me in looking at problem 7. Inverse, I said inverses functions. How about they are inverse functions of each other? Okay, now here in 7, what you have is you would reflect about the line y equals x to be an inverse function. So here's the line y equals x, just as I drew in problem 5, right? Do these reflect about the line y equals x? No, they don't. These, I won't say functions, but they're not even functions, at least one of them. These relations, I will call them, I will say no, comma, these relations do not reflect about the line y equals x. Okay, there it is, y equals x, not reflect. Okay, 9. The tables below show the Fahrenheit temperature equivalent of Celsius temperatures and the Celsius temperature equivalent of Fahrenheit temperature. And then you have 2 tables. It says list 4 pairs of points from the tables that indicate the relationships are inverse functions. And really, temperature conversions, that really is one of the classical inverse function application. Here we have the point negative 25 comma negative 13. And one thing you look for in these tables, you want to have, well, in this case, the degree C here in the initial table for the input value becomes the output value for the second table, and vice versa for degrees Fahrenheit. And you can see that X's and Y's do switch places. So it says list below 4 pairs of points, right? So I'll call this point number 1. Now, they're not, all the things aren't going to be the same necessarily. We can see that's the case here, right? We have a negative, they don't, not everyone swaps, because you're not going to have the same input values for each one. That's the output value necessarily. But here, the y-intercept, 0 comma 32 of the Celsius to Fahrenheit conversion is the x-intercept of this one right here. So that's going to be our second point. Next, we look for the same things. Where do we see things the same? How about this 10 comma, let's just look for numbers the same. 10 degrees Celsius becomes 50 degrees Fahrenheit. So if we input 50 degrees Fahrenheit, we're going to get as an output 10 degrees Celsius. So there we have another point here. So that's 3. And the last one here, we'll just go to these last 2. We have 100 comma 212 will be the inverse of 212. comma 100. So there's would be 4 points right there. I don't know if that's all of them, but these have physical significance also. This one right here, 0, comma 32, 30, comma 0. This would be the freezing temperature of water. And this one here, 100, comma 212, this will be the boiling, called the boiling point. I'll call boiling temperature. Boiling temperature of water. Okay, next. Use the graph shown to answer questions 10 through 12. I will, with consistency, do only the odd number problem, which is 11. Which point would be the same distance from the line of reflection, y equals x, and there we have the line y equals x, line of reflection, as point H. So we identify point H right here, and we're going to bring point H, it's going to be consistently reflected about point B here, because they reflect about this line y equals x. And you can see that diagrammatically they're in the same relative location to the parabolas. This one over here on the H is at the low, the minimum of parabola, and B over here, its inverse rotation, if you want to call it that, is the far left side. So I will say for that one, point B. And that's one reason we're doing 20 problems in this video, because they go pretty quickly. For questions 13 through 16, determine if the function shown on the graph would also be a function. Basically, what we're looking at here is something called I abbreviate HLT. And HLT stands for horizontal line test. Let me abbreviate the horizontal line test. And this illustrates one of the characteristics of inverses functions, that the inverse of a function is not always a function. I'm sure you've heard of the vertical line test if you've been in algebra. The horizontal line test is a test to check if, okay, that's more or less horizontal, this red one here. That's a red horizontal line. And what you can do with this is move it. I didn't mean to move that one, I meant to move the red one. Here we go. You can see that this red line only touches the curve. Looks kind of like a square root function only once. So yes, we'll say yes. And why? One reason we can say is passes the horizontal line test. Okay, next. And you see where what I did is I wrote in determine if the function, if the inverse of the function, yeah, originally I didn't get it right. So what we have here is this. We have this, looks like it's some variation of a absolute value function. I'm drawing my horizontal red line here. Let me try it again. Not the greatest horizontal line, but we'll just have to make it work. So there it is. Touches more than once. So for this one, we would say no. And the reasoning fails the horizontal line test. There we go. Next, 17. For questions 17 through 20, each graph shows a function f of x and its inverse. Determine how the domain of f of x should be restricted so its inverse is also a function. So here's the original function f of x. We can see right here that if x is less than 4, the function is decreasing in value, and greater than 4, the function is increasing in value. So that becomes a point of demarcation. So what we would do is that if we taken together, this f of x would fail the horizontal line test. But if we restrict the domain to greater than 4, or greater than or equal to 4, then we would have a function of its inverse, okay, the red and the purple. And then also if we made this less than x less than 4, less than or equal to 4, we would also have an inverse of a function. So how do we describe that? F of x is equal to, I'm going to put interval notation, greater than or equal to 4 and less than infinity, or f of x is greater than negative infinity up to and including 4, which we bracket off like that. So either one of these domain restrictions will give us a function that is an inverse of f of x. Let's go look at problem 19. Well, again, we look at the axis of symmetry at x equals 5. Describe how the domain of f of x should be restricted so its inverse is also a function. So very similar to problem 17. F of x can be greater than or equal to 5, or f of x can be greater than negative infinity, but less than or equal to 5. So either one of these restrictions will give us a function as an inverse. So I'm just going to do one. If we have greater than or equal to 5, we have this one in red here that I'm drawing. Okay. And this would be its inverse. And I'm now sketching in red here. Inverse of each other. You can see the reflection about the line y equals x. And we need the same thing for the negative one. So x equals 5 is our critical number. Anyway, this is a good way of looking at inverse functions, the graphical approach, looking at tables. Good luck, and thanks for viewing.